Welcome my dear learners for this course on operations research. In this module 3 we were discussing on transportation problems. So far we have solved 4 problems on transportation. Let us move ahead. The problem number 5 of our discussion on transportation problem states that a manufacturer wants to ship 22 loads of his products as shown below. The matrix gives the kilometers from source of supply to the destinations. The shipping cost in rupees is rupees 10 per load per kilometer. What shipping schedule should be used in order to minimize the total transportation cost? So this matrix indicates the kilometers from source to destinations. Per kilometer the transportation cost is rupees 10. What is the minimum transportation cost is what we should determine for this problem. Now if you carefully observe, the sum of supply is yielding 22 whereas the demand is 25. So therefore it is an unbalanced transportation problem. First we should balance it. Then let us find out the minimum kilometers, transportation kilometers, and multiply it with 10 will give us the minimum transportation cost. Let us do it like that. First let me balance this transportation matrix and then let us use Vogel's approximation method to find out the initial basic feasible solution. Come, let us solve problem number 5. If I move ahead to solve problem number 5, we have since we have the supply as 22, I want to add one more excess supply with unit as 3, that will become 25 equals to 25, right? So therefore let me add one more supply and make it equal where the kilometers will become 0 0 0. That is the dummy row which will be used to make it as a balanced transportation problem. Correct? So now the balanced transportation problem will become the source we have S1, S2, S3 and S dummy, and we have the demand, and we have the destinations as D1, D2, D3, D4, D5, and we have the supply, that is 5, 4, 8, 0, 4, then we have 8, 7, 4, 0 and 4, then we have 6, 7, 6, 0 and 5. We left out with 6, 6, 6, 0 and 4. Finally we have 3, 5, 4, 0 and 8. Coming for supply, 8, 5, 9, add 3 to that, it will become 25. That will be equal to 25. So this is the balanced transportation problem. Now for this balanced transportation problem, I should find out which is the minimum transportation cost. We have to calculate what is the minimum transportation cost for this balanced transportation problem. So in step 1, let us use Vogel's approximation method to find the minimum transportation cost. That is, in step 1, I will make use of VAM, Vogel's approximation method, to find the initial basic feasible solution, for which I want the cost, supply and demand. So that will be 5, 4, 8, 0, then we have 8, 7, 4 and 0, then we have 6, 7, 6, 0, then we have 6, 6, 6 and 0, then we have 3, 5, 4 and 0. Coming for the demand is 4, 4, 5, 4 and 8. Coming for supply, the supply is 8, 5, 9 and 3. Let us calculate penalties. Penalty. So let me erase penalty in every step. Due to space constraint, I will erase the penalty in every step and recalculate the penalty as necessary. Penalty is defined as the difference between the least cost and next least cost, that you people already know. Now coming for the least cost is 3, next least cost is 5. So the difference is 2, right? Here the least cost is 4, next least cost is 5, difference is 1. Here the least cost is 4, next least cost is 6, so the difference is 2. Here it is 0. Coming for penalty, here the least cost is 0, next least cost is 4, penalty is 4. Least is 0, next is 4, 4. Least is 0, next is 6. Least is 0, next is 6. Least is 0, next is 3. So we have the highest penalty as 6. Let me go with this one. You can go with this one also, no problem. So now if I go with this is the least cost in this column with highest penalty as 6. So for this cell, I should choose between 5 and 3. Minimum is 3. I will allocate. So this will become 2 and this vanishes. So therefore I cannot allocate in this row further. So that completes step 1. So let me recalculate the penalty again due to space constraint. Now again recalculating, the least cost is 3, next is 5, penalty is 2. Least cost is 4, next least cost is 5, penalty is 1. Least cost is 4, next least cost is 6, penalty is 2. So this is done. Here the least cost is 4, next least cost is 5, penalty is 1. Least cost is 4, next least cost is 7, penalty will be 3. 6 and 7, penalty will be 1. Least cost is 6, there is no difference, 0. Here least cost is 3, next least cost is 4, penalty is 1. So highest penalty is 3. Highest penalty is 3. In this column the least cost is 4. For this cell I should compare between 4 and 9. Minimum is 4. So this vanishes and the remaining is 5. That completes step 2. Now go for step 3. Go for step 3 and recalculate the penalty. So if I recalculate the penalty will remain same here. 3 and 5 is 2. 4 and 5 is 1. 4 and 6 is 2. So this is done. If I come here, 4 and 5, penalty is 1. This is already done. 6 and 7, penalty is 1. Here difference is 0. Here 4 and 3, penalty is 1. The highest penalty is 2. So I'll go with this one. Here the minimum cost is 3. So for this cell, the choice is 8 and 8. So I'll put it as 8. So these two will vanish. So I cannot allocate in column nor in row. Done. Next, go for next step. Recalculate the penalty. Repeat these steps. Now this is done. Calculate the penalty. Least is 4. Next least is 6. Difference is 2. Least is 6. Next least is 8. Difference is again 2. This is done. Here least is 4. Next least is 8. Difference is 4. This is done. Least is 6. Next least is 7. Difference is 1. Here the difference is 0. This is done. So the highest penalty is 4. So least cost among these two is 4. For this cell the choice is between 5 and 4. So minimum is 4. So this is done. I left out with 1. Now recalculate the penalty. Repeat the step. So this is done. difference is 1, difference is 0, this is done, this is also done, this is also done, difference is 1, difference is 0, this is also done. So give preference here, the least cost is 6. For this cell the allocation between 4 and 1, that is 1. So this is done, I cannot allocate here. The remaining is 3, I will allocate here. Done. So if I allocate 3, I are left out with 2. So here also 2, I will allocate here. That completes the allocation. Right. So from Vogel's approximation method, we have got the initial basic feasible solution. So this is the initial basic feasible solution. Let me rewrite the initial basic feasible allocation and the transportation cost what we obtained from VAM. So the initial basic feasible allocation will be, let me write it here. So for step 1, 3. So this is the allocation what we have. 8 plus 4 is 12, 12 plus 4 is 16, 16 plus 6 is 22, 22 plus 3 is 25, correct? So this completes our step 1. I want to go for step 2 and check for optimality, and also if I cross verify, we have the number of allocations as 1, 2, 3, 4, 5, 6 and 7, whereas the m plus n minus 1, that is we have 4 rows and 5 columns, that is 9 minus 1 is 8. Since allocation is not equal to the requirement, it is a degenerate basic feasible solution. So since number of allocations, since the number of allocations which is equal to 7, since the number of allocations 7 is not equal to m plus n minus 1, that is 8, it is a non-degenerate basic feasible solution. This is degenerate. So we have degeneracy because number of allocation is not equal to m plus n minus 1. Number of rows is 4, number of columns is 5, 5 plus 4 is 9, 9 minus 1 is 8, which is not equal to 7. So therefore this is degenerate basic feasible solution. And the initial cost is found to be, how much is the initial cost? Calculate the cost. So the transportation cost is coming for the transportation cost. Let me use space. Basic feasible solution. This is not equal to m plus n minus 1, which is 8. So the transportation cost is turning out to be 3 into 8 plus 4 into 4 plus 6 into 1 plus 4 into 4 plus 6 into 2 plus 6 into 3 plus 0 into 3 whole multiplied by 10, because cost is 10 per load per kilometer, hence the cost will be rupees. How much? The cost will be 3 into 8 plus 4 into 4 plus 6 into 1 plus 4 into 4 plus 6 into 2 plus 6 into 3 plus 0 into 10, which is equal to 920 rupees. Rupees 920. Now I should go for optimality test. So go for optimality. Now moving ahead for step 2, that is for optimality. So if I go for step 2, that is optimality test. Now coming for optimality test, I will go with modified distribution method. That is UV rule. So if I do that, I'll reconstruct this again. We have cost matrix as 5 4 8 0, then we have 8 7 4 0, then we have 6 7 6 0, then we have 6 6 6 0, and then we have 3 5 4 0, right? So this is the cost matrix what I have. Cost matrix what I have. So let me use this cost matrix to find U's and V's. So this is the cost matrix, and the allocation is 8 4 1 4 2 3 and 3. So I'll start with U1 is equal to 0. So U1 is equal to 0. We have allocation here. So therefore V5, right? 1 2 3 4 5, correct. V5 should be 3, right? Cost is 3. So therefore 3 should be equal to U plus V. So that will be 3. Next we don't have any other possibilities because we don't have any allocation. So this is what we call it as degeneracy. So degeneracy is a case where number of allocation is not equal to m plus n minus 1. In such cases we cannot find u's and v's properly because we have one less allocation. In such cases, to break degeneracy, use a small value called delta or epsilon whose value is equal to 0, such that you will find the values of v or u and break the degeneracy and move forward. You should place an allocation of small quantity called a delta or epsilon whose value is 0, such that it should not form loop. Now if I place delta here, what happens if I place delta here? If I place delta here, I can come down, I can come here, I cannot move up, right? But I can come down. So like this, I cannot construct the loop. So I can place delta here. Also I can place delta here. If I place delta here, will it form a loop? No, right? It cannot form a loop. It cannot form a loop. You should place a value of small value of delta or epsilon such that it helps us to find the value of u and v. The placement of delta should not form closed loop. So I can place here, I can place here, we cannot form loop. I can place here also, it will also not form loop. So I can place anywhere. Let me place a small value of delta here. There is no hard and fast rule that you should place a small value of delta. So preferably place delta such that the allocated cell has least cost. Clear? So in this row the least cost is unallocated cells, the least cost is 5. I can place here. Here the unallocated cells we have 2. I can place here also. Delta 4. I can place here and also calculate this one, which yields us the calculation of these 3, and that yields us the calculation of this one. That will yields us the calculation of this and this. That is also correct. No worries. We can place the value of delta here also. That is also correct. Now let me place value of delta here and check. So I choose this and this cell, this and this row, this column in which the least unallocated cell value is 5. I place delta here. Now this will help us to find the value of V1, which is equal to 5, right? So value of cell is 5, U1 I allocated at 0, so 0 plus 5 is 5, correct. Now I can solve completely. So that this is how we should break degeneracy. Whenever you have number of allocation is less than m plus n minus 1, we cannot find all the values of u's and v's. In such cases you should use very small value called delta or epsilon whose value is 0 to break the loop, to break the degeneracy, such that the placement should not form any loop. Clear? So now move forward. Now we have V1, so I can find U2 which is equal to -1. because it is 4, this is 5, so put together it should become 4. Now we have found out u2, I can find v4, since this is minus 1, this should be 7, 7 minus 1 is 6. Since v4 is known, I can find u3, whose value will be minus 1, because 7 minus 1 is 6. Since this is minus 1, v3 will become 7, because 7 minus 1 is 6. Since this is minus 1, v2 will be 5, 5 minus 1 is 4. And finally we have allocation here, so therefore u4 will become minus 7. Done. So we have calculated the values of u's and v's by using a small value of delta. Now calculate the penalty. So if I calculate the penalty, 8 minus 5, 8 minus 5 is plus 3, 6 minus 7 is minus 1, 6 minus 7 is minus 1, then we have 7 minus 5 is 2, 7 minus 7 is 0, 5 minus, sorry, we have minus 1 here, right? So it will become 7 plus 1, 8, 8 minus 5, 8 minus 5 is plus 3, 8 minus 7 is plus 1, 6 plus 1, 7 minus 7 will become 0, 7 minus 7 will become 0, 5 plus 1, 6, 6 minus 3 is 3. Next coming here, 8 plus 1, 9, 9 minus 5 is 4. Then coming over here, 5 minus 3 is 2. Minus 7 we have, it will become plus 7. 7 minus 5 is 2. 7 minus 5 is 2. 7 minus 7 is 0. 7 minus 3 is 4. So you know how to calculate penalty? Because I already solved 4 problems, you have learned how to calculate penalty. So therefore I have not explained in detail, I calculate the penalty. Now if you carefully observe, we have the negative penalty in these two. So therefore there is an optimum solution for this. So therefore I should start from here and form a loop, right? I should start from any one of these two and form a loop. So what I will do, I'll go with this one and form a loop. I'll start here, so I have allocation here, I'll go like this, then I'll come down, and then we have allocation of, sorry, this is already I have allocation, I should not calculate, right? Sorry, I'm extremely sorry, this is 1, we have already have allocation. So go here, then come down, then come like this, then move up. That's form a loop, right? So where I should add theta, minus theta, plus theta, minus theta, plus theta, minus theta. Alternatively I should add plus theta, minus theta, right? So plus theta, minus theta, plus theta, minus theta, plus theta, minus theta. Now what is the value of theta such that the allocation will not become negative? So we have negative points here, here and here. So if I make theta as 1, this will become 0, but this will become negative. So delta is almost equal to 0, so therefore the maximum value of theta that can be allocated such that none of the allocation will become negative is that delta only. So therefore max of theta is nothing but delta. So therefore putting delta, I'll get a new matrix as we have the cost as 5, 4, 8, 0, 8, 7, 4, 0, 6, 7, 6, 0, 6, 6, 6, 0, 3, 5, 4, 0. Again you recalculate as we didn't got any allocation, only the position of delta has been changed, so therefore I should go in for next trial because nothing changed except the position of delta. So delta has been shifted to here. That's it. We have 8, we have allocation of 1, then we have allocation of 4, 2 and 3, 4, 2 and 3, then we have allocation of 3. We are left with one more allocation, that is 4. So delta is almost equal to 0. 0 plus anything will be the same value. Now let us recalculate the values of u's and v's and proceed. So put u1 is equal to 0. Since u1 is 0, I can find v3 which is 6. I can find v5 which is again 3. So since v3 is known, I can find u3. u3 will be 0. Since u3 is known, I can find v2. v2 will be 4 and v4 will be 6. Since v4 is 6, u2 will be 0. Since u2 is 0, v1 will become 4. v1 will become 4. Since v3 is 6, u4 will become minus 6. So we got all the values of u's and v's. Now calculate the penalty. So 5 minus 4 is 1. 8 minus 4 is 4. 6 minus 6 is 0. 7 minus 4 is plus 3. 7 minus 6 is plus 1. 5 minus 3 is plus 2. 8 minus 4 is plus 4. 4 minus 3 is plus 1. So 0 minus of minus 6 is plus 6. Plus 6 minus 4 is plus 2. Plus 6 minus 4 is plus 2. Plus 6 minus 6 is 0. Plus 6 minus 3 is plus 3. So since all the values of penalties are greater than or equal to 0, the solution is optimum. So since all the values of penalties are greater than or equal to 0, the solution is optimum. So hence the answer what we got in the initial basic feasible solution itself is the answer. The answer is 920 rupees, and this itself is the optimum allocation with the value of delta placed here. So hence I'll write it properly, the final answer. 6 into 3 plus 0 into 3. 6 into 3 plus 0 into 3. Let me have some space. 6 into 3 plus 0 into 3 whole multiplied by 10, which is equal to rupees 920, right? So let me write the final solution. So we have the optimum allocation as the optimum allocation will be 58663, 58663, 47765, 47765, 84664, 84664, zeros, 00000. So we have got the optimum allocation. So this is the kilometers from source to destinations, and the units allocated are computed. Let me place them. That is, here we have the value of delta, that is 0. We have 8, 4, 1, 4, 2, 3, 4, 2, 3 and 3. So this is same as the initial solution what we have obtained, just we have the allocation of delta here to make the solution as non-degenerate basic feasible solution, and the minimum cost is found to be rupees 920. After this we have written the optimum answers. Optimum allocation and optimum transportation cost is found to be rupees 920. So this is how you should break degeneracy and solve. In many cases delta might get vanished, that is, if I get plus here and I'll get minus somewhere here, and the value of theta will become 2, then delta plus 2 will become 2, and here it will become 0, 2 will shift here, so thereby the allocation will change and delta get vanishes. In such cases also you proceed, you go with the flow, you will get the solution. So delta might come or delta might vanish. Ultimately our aim is to find out the penalties such that the penalties should be greater than or equal to 0. That will give us the optimum solution and also the optimum allocation. So for this problem, the initial VAM method itself gave us the optimum allocation with optimum transportation cost of rupees 920. So this is the solution for problem number 5. That's all from this lecture. Thank you all.